All right, in this video, we're going to talk about the comparison tests. The first comparison test that we're going to talk about is up on the screen, and you can see that given an infinite series A sub n and B sub n being positive termed, such that A sub n is less than or equal B sub n. Now, this is going to be important just to kind of maybe mention in passing here. This inequality is going to state that this guy here is bigger than this guy here. Okay, so one's big, one's small. And that's true for all n. Now, the comparison test is very intuitive, but it's going to help to go back and remember that when we talk about these types of series, you can plot them as points. Now, I'm not going to plot a bunch of points here on the screen, but instead I'm just going to actually draw a continuous curve to make my point. So part 1 says if the infinite series B sub n converges, then A sub n also converges. Well, remember, the B sub n is the big one. And so if, maybe I'll make that blue, if the big one converges to, let's say, something, and the smaller one is always underneath it, if you will, then of course it's also going to have to converge. It wouldn't be able to get above it, so it would have to converge. Okay? A similar argument can be made down here. If A sub n, which is the smaller one, so my A sub n here, let's say it diverges, the B sub n, which is supposedly bigger than it, would also have to then diverge. Okay, it wouldn't be able to cross back in and settle and have a limiting value. And so it's going to be important to really pay close attention to the inequality that we're going to work with. But you'll see as we look at a couple examples, this is a very, very intuitive test that I personally use quite often when I'm not told specifically how to proceed forward. So let me go ahead and clear the screen. We'll take a couple look at a couple examples. Okay, so we'll take a look at this example, and we're going to move forward using the comparison test. Now, we've had many conversations about looking at functions and identifying the parts that are dominant, or the parts that are going to matter when we're talking about approaching infinity. And so in this particular case, we're going to compare the original function, 5 over 2n squared plus 4n plus 3, to something that's related to it, but something that we know is going to converge or diverge. Okay? So as I look at this, I see that the dominant parts of the original would be the n squared on the bottom. That's going to dominate all of this stuff. So I'm going to investigate now 5 over 2n squared. Well, as you can see, this would have a smaller number than this because the denominator would be increasing. So therefore, our inequality says this. Now, we're not out of the woods yet. We need to make sure the inequality holds for what it is we're trying to do. So I would come over here now and I would investigate the series 5 over 2n squared. Well, that's going to be the same thing as 5 over 2 with 1 over n squared. Now that I know converges by p-series. Since that that p-value up there is bigger than 1, we know that it's going to converge by p-series. Now, let's look at our inequality. This guy's the big one, right? If the big one converges, then of course this one also has to converge. So I'll come down here in summary, say that now the original 5 over 2n squared plus 4n plus 3 converges by comparison. So by coming up with this, by choosing this, that's a great way to start. But we have to make sure, obviously, the inequality holds, and this makes sense. Had we done this but figured out that this diverges, well, if the big one diverges, it's inconclusive as to what the little one would do. The little one could either diverge or could converge. So we have to make sure the inequality holds with the direction that we want this to go. So again, in summary, it would now converge by comparison. Okay, so we'll take a look at another one here. And just like the last one, we're going to take this now and we're going to see if we can compare it to something that we know. Now, in this particular case, I would probably compare it to 6 to the n over 5 to the n. And I know since this denominator is smaller, that my inequality symbol would have to go like this, right? Because this denominator is smaller, this whole thing here is going to be bigger. Now, just to be clear, why I chose what I did is because that's going to be 6/5 raised to the n, which is going to be geometric. So if I look at this geometric series, I know that this diverges by geometric because the ratio, the absolute value of the ratio isn't less than 1. Therefore, we're going to come back and we're going to look at this closely. So we know that the smaller one is going to diverge. If the smaller one diverges, the one that's above it, if you will, must also then diverge. So we can come over here and as a conclusion say, therefore, the original is going to diverge by comparison. So again, the comparison test that we've just talked about is very intuitive. Now again, I have to point out, make sure that when you work these, the inequalities hold in the direction that you can draw a conclusion. Had this been the other way and the bigger one would have diverged, we could not have drawn a conclusion. So we have to be careful once we set this up that we're actually able to make our decision based upon what we selected.